This video is for educational overview only. Viewers are encouraged to study the topic in detail and continue their academic learning alongside this video. Thanks.
We interact with software all day, every day. But have you ever really stopped to think about its environmental cost? We love talking about the cloud. But that cloud isn't some fluffy thing in the sky, right? It's made of millions of servers in massive, energy-hungry data centers. So today, we're going to pull back the curtain on the hidden carbon footprint of the very code that powers our world. So just how big of a deal is this? Well, get ready for this number. The entire tech sector, that's information and communication technology, could be responsible for a staggering 14% of global greenhouse gas emissions by 2040. To put that in perspective, that's about half of what the entire global transportation sector produces right now. Yeah, this is a massive and rapidly growing challenge. And the problem is only getting bigger, especially with the explosion in AI. Think about this for a second. The process of training just one of these big, complex AI models can generate as much carbon as the entire lifetime emissions of 5 cars. That's just wild. It's a huge reminder that every line of code we write has a very real physical impact on our planet. Okay, so if we're going to tackle a problem this big, we first have to understand it. You know the old saying, you can't improve what you can't measure? So how in the world do we actually calculate the carbon emissions of something as intangible as software? Well, it really breaks down into 2 main buckets, which helps us make that invisible carbon visible.
The first part is kind of the obvious one, operational emissions. This is simply the carbon created by the electricity that gets used while the software is actually running. So, think of all the power being pulled by servers in a data center, or even the power used by your laptop or your phone. The more processing your app does, the more energy it needs, which, depending on where that power comes from, means more carbon. Now, the second part is the one we usually forget about, the hidden cost. This is what we call embodied emissions. This covers all the carbon that was coughed up during the manufacturing, the shipping, and eventually the disposal of all that physical hardware. We're talking servers, network cables, processors, the works. Every single piece of gear has a carbon price tag attached to it before it's even switched on, and our software has to account for its slice of that pie.
To try and standardize all this, the Green Software Foundation came up with something called the Software Carbon Intensity Specification, or SCI. The formula itself is pretty straightforward. You take your operational emissions, you add the embodied emissions, and then you divide that whole thing by a functional unit. Now that unit, R, just makes it a rate. It could be carbon per user, carbon per API call, whatever makes sense for your app. The point is, it gives us a score we can actually use to compare different applications.
Okay, so that's the theory. But what does this look like in the real world? Let's dive into a really cool case study from Accenture. They put these very principles into action to see if they could make a real measurable difference. And what they found? Well, it's pretty fascinating.
So here's what they did. They took one of their internal applications and ran it through a software assessment tool to hunt down what it called energy inefficiencies in the code. Then they had their development team spend a month refactoring, basically rewriting all that inefficient code. And finally, they deployed both the before and after versions to measure the difference. Simple enough, right?
So how'd they do? The results were seriously impressive. After they refactored the code, that same automated tool found over 60% fewer energy inefficiencies in the code base. Now this is a huge deal. It proves that these energy-wasting patterns in our code aren't just some vague concept. They are identifiable and, more importantly, they are totally fixable. But check this out, because this is the number that really matters. They saw a nearly 29% drop in energy consumption per user. And get this? The application actually had more users after the changes, but it used way less energy for each one of them. This proves that optimizing your code for sustainability isn't just a nice idea. It has a real, tangible impact on how much power you're burning.
That Accenture story shows us that how you write your code makes a big difference. But what about the language you write it in? This leads us to a really interesting and, let's be honest, kind of heated debate in the software world. This idea that your choice of programming language is one of the biggest factors for how green your software is. But is that really true?
You see claims like this all the time, right? At tech conferences and blog posts. This quote here, from a keynote at a major conference, suggests a massive 75 times difference in energy use between 2 languages. And this isn't just talk. This idea is actually guiding huge business and technology decisions at major companies.
And this belief is fueled by studies that come up with these kinds of rankings. They'll run the same little problems in a bunch of different languages and then measure the results.
And yeah, when you look at a table like this, you'd probably conclude that languages like C and Rust are super efficient, while a language like Python is, wow, over 75 times worse. But there's definitely more to the story. So this just makes you wonder, doesn't it? The original studies, they found a connection, a correlation between a language and how much energy it used. But we all know that correlation is not causation. Is the language itself really the reason for this huge difference, or is there something else going on under the hood? First off, we've got to make a really important distinction here. We're not actually comparing abstract languages, we're comparing their specific implementations. Think of it like this: the language is the recipe, but the implementation is the chef. You can have the exact same recipe, but different chefs are going to cook it with different levels of skill and efficiency. C has different compilers, Python has different interpreters, and they can all perform in wildly different ways. And here is the real kicker that newer research has uncovered. The little programs they used in those original studies, they weren't really equivalent. Specifically, they had completely different levels of parallelism. So some versions were written to use multiple CPU cores at once, all hands on deck, while others were just chugging along using a single core. And that's a property of the code, not the language itself. So what happens when you control for these things? When you make sure you're actually comparing apples to apples? Looking at how many CPU cores are being used, the whole picture changes. The research concludes that the choice of language has no significant impact on energy consumption beyond its effect on how long it takes to run. Let me say that again more simply. The most energy-efficient code is just the code that runs the fastest, period.
So, if it's not about just picking the right language off a list, what are the real levers we can pull to make our software more sustainable? Let's get into the stuff that actually works.
The SCI specification really boils it all down to these three core strategies. First, energy efficiency. Just make your code faster and more performant so it uses less electricity. Second, hardware efficiency. Use less physical stuff, fewer servers, less memory to get the same job done. And third, something called carbon awareness, which is a cool idea about running your code at times or in places where the electricity grid is powered by more renewables.
And this brings us to a really powerful final thought. For decades, software developers have been obsessed with performance, right? Making code run faster, use less memory, be more efficient. What if, this whole time, without even realizing it, they were also practicing green software engineering? This completely reframes the conversation. It suggests that the path to making our software sustainable isn't about learning a whole new set of confusing rules, but it's about doubling down on the principles of just excellent, efficient engineering that we've cared about all along.